Thank you, Clifford. Okay, I come to my final lecture, and I appreciate all the students who thank you, Jacques. Thank you so much. I've enjoyed my week here, and particularly I have enjoyed talking to many of the students. Perhaps I have one request to make, which is after the lecture, perhaps I could have my picture taken with the students. Not the other lecturers, but only the students. Now, as I came to my final lecture, I am sure that many of the other I feel the same way as some of the other lecturers, namely a sense of, I'm both happy that I'm able to teach you a little bit of quantum field theory, but at the same time a tremendous sense of frustration because there's just so much to cover, and I've managed to cover only a tiny bit. So the good news is that hopefully the people would eventually get my book out of the customs, and you can look at the book. So everything I talk about is in the book, and in my book, and I'll give page references. Now, over the weekend, I started writing transparencies, but when I talked to some of the students and when I talked to Clifford, I realized that some of the students, it would be better for the students to have me write on a blackboard. So actually, this lecture, what I'm going to do is that after talking to students over the weekend and to Clifford, I stopped writing my transparencies. So I have several sheets of transparencies. So this talk is going to start out using transparencies, and then I'll switch to the blackboard. Okay? So I'm sorry, the ink, I think the weather, somehow, I don't know what happened to the ink. I just wrote it yesterday morning. It's already like this. Okay, so I will pick up where I left off last time, right, on Friday. I introduced the notion of symmetry in a field theory. So we have our good old scalar field that we discussed in this course. And phi of x, remember, I can then go to a complex version of phi of x. I discussed this on Friday. And the symmetry is that the field can be transformed by multiplying by a phase e to the I theta. And the Lagrangian I wrote down is clearly invariant, does not change because here's a phi and here's a complex conjugate, Hermitian conjugate, so the phase cancels out. Now on Friday, I alluded to the fact that theta must be independent of the space-time point x. So what happens, you can ask, this is one of the great questions in physics. Phi of x goes into the e to the I theta of x, phi of x. Suppose theta depend on x, the phase that you multiply with. This is called a local symmetry in contrast to a global symmetry. Local means that you should be able to make a different phase transformation at different points in space-time. Well, we see immediately that this Lagrangian, in this Lagrangian, some of the terms are going to be invariant, but some of the terms are not. So clearly, phi dagger phi is invariant because in the phase cancels out. But the derivative term is the one that gives us trouble. All these two terms, any term of this form you write down would be invariant. Notice the derivative of phi. If I take the derivative of e, it goes into e to the I theta phi. And now when I put the derivative across, of course, I also have to differentiate on e to the I theta. So this is not invariant. So remember that last time on Friday, we discussed this point carefully, that it was crucial that we were able to move the derivative past the field transformation. So it's not invariant. So how do we make it invariant? You see that suppose we invent a field, a mu, a vector field with a Lorentz index mu, such that under transformation, a mu goes to this. Then you see that if I form this combination, right, then this d mu phi has this extra stuff, But if A mu also transformed by this extra stuff, then in this combination, this extra stuff would cancel out. And this becomes e to the I theta d mu phi. And if we use this capital D mu, which is called a covariant derivative, so in contrast to the ordinary derivative, it has an extra term. And I'm sure that Professor Marov is going to discuss with you the covariant derivative in general relativity. And there's a deep connection between the covariant derivative of local symmetry and the covariant derivative in general relativity. There's a connection there. So if we replace, therefore you can see that if we replace d mu phi in this Lagrangian, instead of this Lagrangian with ordinary derivative, if we were to replace it by a covariant derivative, then the Lagrangian would be invariant. Okay. Now, in particular, let's try to remember how A mu transforms in this way. Okay? So the transformation of A mu is forced upon us. Okay? This is not up to us to choose. The theory forces it upon us. So A mu transforms in this way. Now, we can, of course, take the derivative, and we take the derivative, then we get this second form d mu theta. Okay. Now, this is a little bit of a tricky step I want you to realize. So this is why I have a purple arrow pointing to this equal sign. Most textbooks, almost all textbooks, immediately write it in this form. This is somewhat misleading because this equality is not strictly correct. Because although these two forms look to you as if they are equivalent, just a result of differentiating, this is actually a better form because it keeps the information that theta and theta plus 2 pi is in fact the same thing because the transformation was e to the I theta. Okay? So this transformation is known as gauge invariance, and it is one of the most important concepts in quantum field theory, Okay? And this is discussed in great detail in chapter 3.4 of my book, so as soon as somebody can get the book out of the shipment of books out of custom, you can read about it in this chapter. So, now the interesting thing is that, remember in my lectures last week, I introduced a Lagrangian for a spin 1 field A mu. And in fact, I even used the same notation, A mu, as here. Okay? So, you would say, okay, very nice. We already have a ready-made Lagrangian for A mu. We don't have to go out and buy another Lagrangian from the store. We already have one at home. So we just use the Lagrangian that I wrote down last time, which was this. You remember, I actually derived this Lagrangian. Now, one thing you notice immediately is that if A mu transforms like this, it transforms A mu plus some extra stuff, then this is obviously not invariant. Right? So if A mu transforms like that, this is not invariant. So therefore, the only way it can be invariant if the coefficient is 0. So it's unless the mass is equal to 0. So therefore, you can see that gauge invariance forces the photon to be massless. The spin 1 field last week, we interpret as the photon. So therefore, one of the important concepts in physics here is gauge invariance implies that the photon is massless. Okay? So let me pause for 1 second and ask if there are any questions. And everybody understood this point? This is a very important point to understand. Now, the other thing you remember is that F mu nu is d mu A nu minus d nu A mu. Now, we can check if this term is invariant, whether it changes or not. So we calculate a change of F mu nu. Well, according to this, A mu changes by d mu theta. So therefore, the change of F mu nu is d nu theta minus d mu theta. So we're just taking derivatives in two different orders and subtracting. And so this is equal to 0 according to Mr. Newton and Mr. Leibniz. So in fact, this Lagrangian is invariant if we don't have this term. So this is an explanation, a deep explanation of why the photon is massless. Okay. Now, on the next transparency, I'm going to try to do something a little bit more ambitious. I'm actually going to try to teach you a little bit of mathematics. The reason I wanted to do that, so I wanted to give you a very fast, a quasi-instantaneous introduction to the theory of mathematics of differential forms. Again, so for more detail, you can read about this on page 218. Okay, so the mathematics, the reason I want to introduce differential forms here is that it's because it is really the natural language to discuss Yang-Mills fields. So that is what I'm going to discuss next, Yang-Mills, non-abelian gauge fields. And also differential forms are very important in string theory. For those of you learning string theory, you have to learn differential forms. So differential forms is I'll explain what it is. So there's no reason to be afraid of differential forms. It's really very simple stuff. Okay, so let x mu be d real variables, and a mu be d functions of x. So in fact, if you like, you can think of x mu as the coordinates in d-dimensional space, in capital D-dimensional space. Now let us just call this object a mu times dx mu a one form. So I give it a symbol capital A. So this thing is called one form. And this object here is the infinitesimal of Newton and Leibniz. But we're going to go on and discover its properties. Okay. Now, unfortunately, the ink is, for some reason, my pen doesn't work very well. So I hope you can read this. But if you can't, maybe I'll write it out on the blackboard. Okay. So if I make a transformation of x goes into x prime of x, then dx mu is then equal to dx mu dx prime nu dx prime nu. Okay? So the one form A is equal to a mu dx mu. So I just plug in dx mu here, right? So a mu dx mu dx prime nu dx prime nu. But this is supposed to be equal to, this is the definition of a prime in a new system of coordinates. So this is making a coordinate transformation. So by definition, this is a prime. So therefore, we see that a prime nu is equal to this. So in fact, as I've written here, a prime nu is equal to a mu times dx mu dx prime nu defines a vector. Now, can people actually see this? Because I can see it up here, but people in the back perhaps have some trouble. Okay, it seems that people can see it. Oh, no, it's okay. Thank you. Yeah, I think it would just, let me just press on. Thank you. Define also a p form. This is called a one form, but in general, for some other integer p, I can define a p form. So as you can imagine, a one form has one of these dx. A p form has p of these, and then multiplied by something that has p indices. So actually, as you could guess, that the one form, this is a vector, and this p form is would transform like a tensor. Okay? So as you learned in school. So this is really the whole idea of differential forms is really a fancier way of doing vectors and tensors. So for example, a two form, let me write this down. Okay, so two form is defined as something with two indices. And so a two form is 1/2 f mu nu dx mu dx nu. So at this point, I can use any letter I want, right? I use capital F. But of course, later on, it would turn out that these has something to do with electromagnetism. But at this point, I'm just doing mathematics. So this is just any letter you want. So the fact that I've written in terms of f mu nu at this point has no significance, and use the letter F here. So similarly, theta would be a zero form if a zero form would have no dx associated with, so just a theta. So just an ordinary function of x is a zero form. So zero form is just a fancy language for an ordinary function. Okay. Now an important point is that I haven't told you how these dx's are to be multiplied together. Right? In this expression, I've written a lot of dx's, and it looks like they are multiplied together. So I haven't told you the rule for multiplying things together. Now, in mathematics, we choose the definition. We make the definition so that things work the way we'd like it to work, if you like. That's one of the approaches. So let me motivate how we're going to define this multiplication by going to a very, very simple example. Let us just go to two-dimensional space, and let me call the coordinates x mu, just x and y. Okay? And then we ask how dx, dy transform. So dx transforms into dx prime plus dx, dy prime, multiply by the same thing, a similar thing, except differentiate with respect to y. So we get here four terms, right? Because there are two terms here, two terms here. You see we get dx prime from multiplying this one with that one. If I multiply this one with this one, I get dy prime, dx prime. So we get four types of terms. So we get a big mess on the right-hand side. How are we going to make this mess simplify? Okay, this is a very ugly mess on the right-hand side. So the thing to do, the very nice thing to do, is we postulate these differentials as anti-commuting objects. Okay, so later on in this course, that you would hear about supersymmetry, and from Professor Gates, who has just arrived. I don't know how he can be dressed so elegantly. Oh, okay. Since I walk up the hill, and I'm already completely soaked in sweat. And so if we postulate these things as anti-commuting objects, and sometimes they're called Grassmann objects, and you hear a lot about this in the second half of this school. They are related to supersymmetry and superstrings and so on. If you were to do this, then you see that these terms, dx prime, is 0, right? Because if they anti-commute. And this is equal to 0. And this is equal to minus that. So therefore, if I only have one object out of these four objects survive. Only one object survives. So this is dx prime, dy prime. And so it's multiply them by this, as you can see by, if you just look at this. But you see, this is very nice if you choose them to be anti-commuting objects, because you recognize that this is just the determinant of the transformation, namely the Jacobian. So therefore, what we learn is that these differentials, in the theory of differential forms, these differentials have to be treated as anti-commuting objects. Okay? Let me pause to ask if any questions from the students. Yes?
When you write the two form f is equal to a half f mu nu
right.
dx mu dx mu, I'd just like to know what dx mu and dx mu actually symbolize. Is that like a basis or?
Yeah, okay, that's a good question. So if you see from this example, you see dx dy, it's like a little area element. You can think of dx as some infinitesimal here, and dy as some infinitesimal in some other direction. So dx dy is something like the object that characterizes this area element. Okay? So in ordinary calculus, where you learn in school, people will write some integral like this. And it doesn't matter whether you write this in this order, dx dy or dy dx. But mathematically, you see that in some sense, the area element has a direction, because it's actually the thing. You can imagine a vector pointing up from this element, or the vector pointing in the opposite direction. So for this simple area element, it's kind of trivial. But when you go to higher dimensional space, when you go to string theory, and when you start manipulating objects in higher dimensional space, then these differential forms become very important. Okay, question?
What is the effect of postulating that those objects are anti-commuting?
Did you say approximating those objects? No, postulating. Yeah, okay. Well, if you don't postulate, it's only if you postulate that you, if you don't postulate this, you would get a mess on the right-hand side, as I explained. So that's a practical answer. The more abstract answer is that these products of differentials are like area elements, and when you generalize them, they're like volume elements, and in higher dimensional space, they're higher dimensional objects. So clearly, we want dx to be 0. Okay? So this is very different from, I mean, just to add a footnote, which may or may not confuse some of the students, but perhaps it would help some of the students. This is very different from the kind of metric that Professor Ellis and Professor Maroff have been writing down. In the metric, it's a different story. It's a length element. Okay. Any other questions from the students? Okay. So, I'm almost finished with the mathematics and ready to go on. This will be the last transparency of mathematics. So the next step is we'd like to define a differential operation, a little operation called little d, that would act on any form. So by definition, if you give me a form, a p form, so I've written it out again here, h is equal to this h mu1, mu2, mu p times dx mu1, dx mu2, dx mu p. By definition, we say that little d acting on h gives us a p plus 1 form. Okay, so this is a definition of dh. So what is dh? We define dh. I'll tell you what dh is. dh is, if I take this object and differentiate with respect to d nu, and then multiply by dx nu on the left. Okay, so dx nu times all of this stuff. So that's the definition. Okay? Now, so if we define this object d in this way, then we see that if we have a one form, capital A, then you see what dA is. dA is d nu, a mu, dx nu, dx mu. Okay? But since dx nu, dx mu, we just discovered, should be treated as anti-commuting object, right? So therefore, this is anti-symmetric under interchange of nu and mu. If I interchange nu and mu, I should get a minus sign. So therefore, I can take this term and reverse mu and nu with a minus sign and divide by 1/2. So this is d nu a mu minus d nu mu a nu. Okay? It's equal to this. Okay? So when I asked if people in the back can read this, everyone nodded their heads. So I assume people can read this. Unfortunately, this is particularly bad. Now, you see, so far, it's all mathematics. But sometimes, in the history of human thought, it is really amazing, as I said in my popular lecture, as Wigner remarked. He wrote this article, The Unreasonable Effectiveness of Mathematics in Describing the Physical World. Sometimes mathematics and physics really converge. And so it is really remarkable that in the theory of differential forms, these objects arise. But we see that this reminds us, it should remind you of what you learned in a course on electromagnetism. Because if we think of capital A as the electromagnetic gauge potential, then F equal to dA, you see, this is just the electromagnetic field strength, because you learned in school that F nu mu equal to d nu a mu minus d mu a nu is exactly the electromagnetic field, namely the electric field and the magnetic field. Okay? So you see that if I define f to be equal to this, then f nu mu is just equal to this. So you see what took Maxwell along, this was originally, as you remember, was discovered by many, many years of difficult experiments by people like Ampere and Biot and Savart and so on and so forth. But it is really quite remarkable that the mathematical structure coincides with what mathematicians discover as the theory of differential forms. So I will let the other professors in their course explain to you in string theory and in relativity what some of these deep connections may be. But you can see from here that there is a deep connection between geometry and gauge field. So I'll just leave this as a remark, which you can ask the other professors. Okay. Yes?
Just a comment.
Yes.
Notation is crucial in all of this.
Right.
And in some of the literature on the relativity side and maybe the differential geometry, you would have a little wedge operator between the D's.
Right.
And that may sort of help one see it's not just an ordinary product.
Right. Well, in this book, I actually have one paragraph denouncing people who introduce useless notation that clutter up, that serves no purpose but to clutter up the page. I can refer you to where I make this remark. So I think in physics, we constantly try to simplify our notation, which I think actually allows us to see things better. And I just talking to the students the other day at lunch, I expressed the opinion that it's not an exaggeration to say that Einstein's great contribution was to introduce the repeated index summation notation, and Dirac's one of his great contribution was the Bryan-Ket notation. I mean, all these notational advances. And as I said in my popular lecture, Maxwell originally have something like, I don't know how many equations. I asked the students if they know why the magnetic field is named H. Maxwell didn't have vector notation, wrote all the components out. So I really think dropping the wedge is a good idea. So other questions? Okay. So homework exercises. So as Professor Clifford Johnson last week told you guys must work. This is not a holiday camp. So I agree with him. It may be a holiday camp for the lecturers, but not a holiday camp for the students. So here are two homework problems that you should do, which is actually done in a book, but since we don't have time to do this in detail, sure. Sorry? Clifford is here. I thought you went out. Okay. So I don't have to be tough. Clifford can do the tough talk for me. Okay, so exercise 1 is show that dd is equal to 0. That means if you act with this operation d and you do it again, you get 0. Exercise 2 is that from exercise 1, it follows that if f is dA, then df must be 0, right? Because if I act with df, I see dd. So show that the exercise is to show that this implies half of Maxwell's equation. So half of Maxwell's equation just pop out. Okay, so it's at this point, Clifford told me not to write any more transparencies. He told me to go back to my room and relax and not sit there and write transparencies. So my last transparency is going to be just a quote from C.N. Yang. So C.N. Yang, in his autobiographical book, was talking about an idea that he first had as a student and that he kept coming back to year after year. So I've underlined this word, student, in red, okay? So you are the future of physics, of theoretical physics, not the lecturers. Most of the lecturers are about to exit from the stage. And you are the future. The lecturers, many of us, represent the past. So student, he had the idea when he was a student, not when he was a professor. Okay? So the same thing with Newton, with Dirac, with 't Hooft. You know, 't Hooft had some of his greatest ideas as a student. Okay? So I've underlined this. So he said, most such ideas, he was referring to a very nice little idea, which I would explain to you in a few minutes. This is the idea that led to the Yang-Mills theory, or the non-Abelian gauge theory. So he said he had this idea first as a student, and that he kept coming back to year after year. And he said most such ideas are eventually discarded or shelved, but some persist and may become obsessions. Occasionally, an obsession does finally turn out to be something good. So for the students here, I underlined two words. One is student, the other is obsession. Okay? So in physics, you have to be obsessed with something. In many cases, it would just turn you into a nut to be avoided by all other physicists. But you should have some ideas. It may be crazy, but you should persist, and it may turn, as he said, most of them become just obsessions. But some of them eventually may turn out to be something good. Okay, so I tell you about this little idea that he had. And in hindsight, so I'm going to switch to the blackboard at this point. Thank you, Clifford. Okay, so it's really very, very simple. The idea is just extremely simple. So you remember at the beginning of this lecture, I talked about what if a phi of x goes into e to the I theta x, phi of x. Okay. Now last time, so where phi is a complex field. So last time on Friday, I talked about the notion of symmetry when we introduce many, many fields. If we introduce more than one field, I don't mean many, many fields. So suppose phi of x is actually a collection. So that, again, is, goes back to Werner Heisenberg, as you remember. Phi n of x. Okay? So we have n complex scalar fields. So let each one of them be complex. Okay. And last time, I asked the students to learn a little bit of group theory by reading the appendix of my book. And also Clifford then made some of the students teach each other group theory. So I assume that by now, since 3 days have passed, that you've all become experts on group theory. So Yang's idea was the following. Phi of x, suppose phi of x goes into u of x times phi of x. With this phi of x, we are generalizing to this phi of x. So this notation actually means a collection of n complex scalar fields. Instead of one complex scalar field, we have n complex scalar fields. So then this is an n by n matrix. Okay? But just like e to the I theta has the property that if I take the complex conjugate, Hermitian conjugate, I'll just write Hermitian conjugate here. This is equal to 1. This matrix U has the property that U times U dagger is also equal to the identity matrix, n by n identity matrix. And also, we impose the additional condition that determinant of U is equal to 1. And this defines the group SUN. And the students I noticed at tea time on Friday, they were teaching each other SU2. So some of you may have already learned SU2. So for the purpose of this lecture, actually, you don't have to think about SUN. You can just think about SU2 if thinking about SUN is too difficult. So in 1954, by that time, so Yang had this idea. He was a student during the war in China, but by 1954, he was already a well-known person in the United States and was at Princeton. And in the summer, he went to Brookhaven, and he shared an office with Bob Mills, who is a very nice person, by the way. And the two of them worked out the details of how this theory would work. So in hindsight, by the way, now we can do it all in a few pages, but at that time, Mills told me that it was very, very difficult. Yang did not know how to construct F mu nu. But you would see that it would be very obvious nowadays. Okay. So let me ask. Yeah, good. I was going to ask for questions.
I was going to ask, we are proposing that the matrix U has SU and symmetry. Is that's what they imposed? Or that's what they wanted?
Yes.
So could we pick another symmetry group and get...
Yes. There are many groups that are known to mathematicians. There are some of you may have heard of SON. I'm sure you have heard of SO3, the rotation group. And there are more complicated groups called symplectic groups, and so on and so forth. You can write down a field theory for each one of these groups, and even more complicated variations of groups and so on. Yeah. But I'm just sticking it to one. I'm just, for simplicity, talking about one type of group. Okay? Other questions? Yes?
Less influence, your choice of the group for you.
Oh, so yeah. So this lecture is actually very mathematical and theoretical. So I'm just laying out the theoretical framework. So ultimately, which group you choose has to do with experiments. The experimentalists have to tell you which group you choose. Now, these lectures at the school are not all completely in the right order, because I understand that Professor Martin already did some Yang-Mills theory for you, and not only that, he already did a lot of phenomenological particle physics based on this theory, SU2 cross U1 and SU3 and so on. So historically, in the 1954 paper, Yang and Mills only wrote it down for SU2, in fact. But then later it was generalized, and then we now know experimentally that almost all nature, except for gravity, is all described by a Yang-Mills theory, but with different groups. So the electromagnetism and weak interaction are now unified in SU2 cross U1, and the strong interaction is unified as a SU3 gauge theory, and then these three interactions could all be unified into an SU5 gauge theory, or as this young lady suggested, doesn't have to be SU groups. In fact, there's also an SO10 theory, a theory based on the group SO10. Okay, so what group? There are two answers to your question. One is experimentalists have to find out what group is the right group, and the other is to take the philosophy that Einstein expressed, and which I explained in my popular lecture, which is to know the mind of the creator. So if you know the mind of the creator, you can also do that. Yes, Clifford.
This is, of course, something that you should all, as young developing physicists, be aware that you have to make connections between different things that you've learned. So you should now be able to refer to the notes that you've been making from Professor Martin's lectures and see that he's been giving the experimental, or what's called phenomenological, complement to this discussion, where he does indeed describe some of the things that people have actually seen in real experiments which motivate some of these choices. So you're hearing about these things at about the same time, and you should be mature enough to start beginning to make connections between these things. So go and refer to his notes, and also he has a little lecture today where he'll talk more about these things, and now you see the connection between these two topics.
Right. That's a very good comment. As I said, Professor Marov would be here for a few more days, so you should keep asking him, because there's also a connection, as I said, between geometry and gauge theories and gravity, and he's talking about general relativity. In general relativity, there's also a covariant derivative, and you should ask him the connection between the two kinds of covariant derivatives.
Discuss this with the students, but it's not part of our lecture.
Oh, okay. He would be happy to tell you about covariant derivatives. Okay, so now, in hindsight, as I said, everything is always easy in physics, okay? So, in fact, at this point, all we do is repeat everything we talked about half an hour ago, okay? So half an hour ago, we talked about multiplying by phase, and now we just have this more complicated thing. So it's very simple. So now what we want is to construct a Lagrangian okay? And clearly, we see that phi dagger phi is invariant because phi dagger phi goes into phi dagger u dagger phi, which is equal to phi dagger phi from this property, okay? I suppose I should start using color chalk. Okay. Okay? So therefore, any function of phi dagger phi is also invariant. Now, but just as in the beginning of today's lecture, d mu phi dagger is not invariant anymore. Okay? And in fact, d mu phi, just a matter of arithmetic, we can write down. Let me do it here. Oh, let me do it over here, maybe. Okay, so d mu phi, we just differentiate, goes into d mu u phi. Okay, and we're going to take a u as an overall factor. You see that this is d mu phi plus u dagger d mu u phi. Right? So we have this extra junk. So with this extra junk, you see that d mu phi transform with this extra stuff, and it's not going to be d mu phi dagger, d mu phi will not be invariant. So we have to do something else. And of course, by now we know what to do. We introduce a covariant derivative. Covariant derivative. So it's amazing in physics how some of the most brilliant ideas, in fact, that's almost a definition of brilliant idea, which is that in hindsight it should become trivial. There are ideas in physics that sort of 30 years later, still, when it was introduced, it was messy and complicated, and 30 years later, still messy and complicated. You know some of those ideas are not such great ideas. So once again, we introduce a capital D mu phi, defined as D mu phi minus A mu of x phi of x. So just like what we did before. And we make this A mu phi transform in such a way as to cancel this mess. So we see immediately that A mu is equal to u A mu u dagger minus I d mu u dagger. Okay? So if you can check for yourself. So this is another exercise. Perhaps I'm not going to do the arithmetic for you. Check that d mu phi dagger d mu phi now becomes invariant. Okay, I'm not going to do the arithmetic, but roughly speaking, you can see how this works, that you're going to introduce this extra term in the transformation of A mu will cancel this extra junk that we have here. However, I have to tell you an identity. Okay. So the identity is the following. Let's recall that u dagger u is equal to the identity matrix. Okay. So now if I were to take the derivative of this equation, I get d mu u dagger u plus u dagger d mu u is equal to 0, right? Because the derivative of the identity matrix is, of course, 0. So therefore, I see that I actually have the reverse convention in the book. Okay, so bear with me. Of course, you can always reverse U and U dagger. It doesn't matter. It's a dagger, just the Hermitian conjugate. So if I write it like this, I interchange the dagger and the non-dagger. Then we see that this thing is minus that thing. Therefore, this is also equal to U A mu U dagger plus I U d mu U dagger. Okay? Okay? So this is how this thing should transform. And this object is a very important object in modern physics. It's called the non-Abelian gauge potential. Okay? So let me ask if the students have any questions. So see, the transformation can be written in two different forms. And it is in the second form, you can see that it cancels that thing. There's this thing here is U dagger d mu U. Oops, I think I have some mixed up. So I leave it as an exercise for the students to straighten out the problem here. I seem to have some problem with the daggers. Okay? So are there any questions? Okay, so this is a non-Abelian gauge potential. Now we can immediately see that there are various properties to this non-Abelian gauge potential. First of all, we see that A mu has to be an n by n matrix. They're n by n matrices because U and U dagger are n by n matrices. So if you multiply them out, they're obviously U by matrices. And you can also show that the condition, if I impose, if I look at this object, A mu minus A mu dagger, this transforms in such a way that I can impose A mu minus A mu dagger equal to 0, which means that A mu is Hermitian. These are all technical details, and so let me not, since I'm running out of time, let me not go into all the details here. Okay, now one important remark is that we should see that this reduces to all the work we did earlier. And if we have U is not a matrix, if U is e to the I theta, not a matrix, right? So this reduces to the simpler case we have earlier. We should get back what we had before. Well, you can see that from here, this box reduces to A mu goes into A mu. This first term, if this is just this is e to the I theta and this is the complex conjugate, and they're just numbers, it just cancels out. So, okay. Now the second one, this d mu U just becomes I times the d mu theta, so it just becomes d mu theta. So this is a check, okay. Okay, so with this covariant derivative, we are in business, right? We can now write down a Lagrangian, which is invariant. So our job was to construct the Lagrangian. So to pause, the Lagrangian is then d mu phi dagger, d mu phi, plus minus any function of phi dagger phi. This would be invariant. Okay, let me pause and ask you any questions.
Did they get the Nobel
Yes?
Prize for this paper?
No, there's no Nobel Prize, but Yang has been saying for some years that that there should be a second Nobel Prize. So are there any questions? There's a very interesting historical footnote. Mills is a very modest guy. He's a very likable and modest guy, and he was a professor at Ohio State. Unfortunately, he passed away a couple years ago. And he freely admits when he talks to people that this was completely Yang's idea, and it was just his good fortune to share an office with Yang. But then, a couple years ago, some senior person at Brookhaven told me an interesting story, which apparently is true. That summer at Brookhaven, actually, 3 people shared the office. There's a third person. And the third person just didn't know what was going on. So he shall remain nameless. Okay, are there other questions? By the way, there's also a complicated history to the discovery of non-abelian gauge symmetry. There's a very nice book by the Irishman O'Rafferty, which you should look at if you're interested in the history of gauge theory. Yes, question?
You just actually spoke to the point. I was going to ask you to elaborate a bit on the history.
Right.
Shaw's name is in there.
Sure.
And
so O'Rafferty has a very detailed discussion. Incidentally, David Gross wrote a paper in which he claims that Klein does not deserve any credit. He said the David Gross paper was very strange. It starts out by saying, I was invited by the Swedes to attend some conference in Sweden, but the whole conference was so boring that I couldn't stand it anymore, so I just went to the library and looked up Klein's paper, and I decided to study his paper, and therefore I wrote this historical paper.
confusing as to whether he actually has the ideas, but it's close.
Okay.
Could you perhaps point out the unusual spelling of O'Rafferty so the students, so if they're looking it up?
I'll try.
Not at all. Well, it's probably in your...
No.
Never mind. I'll look it up, but it's up because if you're looking for it in the library, you
Okay. Okay. Since I'm running out of time, let me press on. Okay, so now at this point, as Clifford Johnson said, I'm going to start making contacts with Professor Martin's lecture to some extent. But let me now press on with the story, so let me try to make it as exciting as possible. If you think of this, Professor Johnson told you not to be talking about television drama, but if you think of this as some kind of thriller, then what happens? So Yang has thought about making this thing to generalize the construction of electromagnetism to this construction. And then we arrived at this transformation law and the covariant derivative, and we're able to construct this Lagrangian. But what about the dynamics for A mu? Okay? So at this point, this is like, suppose you had, in the beginning of this lecture, we had found the coupling of A mu of the photon field, of the electromagnetic field, to the scalar field, but we don't know Maxwell's Lagrangian. So we have to ask what is Maxwell's Lagrangian. How do you construct the analog of Maxwell's Lagrangian? Now you have to construct a Lagrangian for A mu, right? So the first step is you need to construct the analog of F mu nu. Okay? So F mu nu is going to be more complicated, and if we construct the right F mu nu, then we can construct the Lagrangian. Okay, so if you look at Yang and Mill's paper, they do it in a very, very brute force kind of way. And if you find that this was apparently what took Yang many years to construct was how to construct F mu nil. And if you look at their paper, you see it was done by trial and error. They just tried this and they tried that, and they so on and so forth. So here's why I introduced differential forms. Differential forms, with differential forms, things become much, much simpler. Okay? So we are going to use, so Yang and Mills, they used brute force trial and error. Okay? But instead, what we're going to use, since we're so much more sophisticated than Yang and Mills, all of you, because you just learned differential forms, we're going to use differential forms. Okay. Now, A is equal to A mu dx mu, the differential form. It is now a matrix. So this is actually a matrix 1 form. Well, that's a small generalization from what I already taught you. I told you what 1 forms are. And it's just a 1 form that also happens to be a matrix. There is an additional trivial thing that I have to mention to you. This is completely trivial, which is that it's very convenient, and that mathematicians use. It's better to multiply what physicists you call the A mu by minus I. It turns out the equations become simpler. This is trivial, of course. You can take somebody else's A mu and multiply by square root of 17 if you want, right? So you can certainly take somebody's A mu and multiply it by minus I, and that's what mathematicians do. If you read the mathematical literature, this is what they do. Okay, now if you do that, it turns out that just some i's and so on drop out and so on. Okay, our task is to construct a 2 form out of A. Okay? So this is our job. So apparently, as I said in the story, Yang himself struggled for many years as he first thought about this as a student. And then apparently the story was that Yang and Mills together, they spent the whole summer doing it. But you students are so sophisticated that you're going to do it in 30 seconds. Okay? So, because we now have a superior notation. Okay, we want to construct a 2 form. Well, if we're given a 1 form, a 2 form is just dA, right? If we apply d on A, that gives us a 2 form by definition. So this is a 2 form. Okay? Now, what other 2 forms are there? Well, it's a 1 form, so A square is also a 2 form. Okay? There's a 1 form times a 1 form. That is all. Those are all the 2 forms. That's all the 2 forms you have. So the answer, which took people years to find, is you can do in 30 seconds. It just has to be a linear combination of dA and A square. And in fact, the answer is dA plus A square with the suitable normalization. Of course, the relative coefficient, just how A is normalized. If you had multiplied somebody else's A by square root of 17, some 17s would appear. Okay? But that's the answer, dA plus A square. Okay. Now, I'm going to come back and talk about this object A square a little bit. Okay? How come when you study electromagnetism, if you had a very sophisticated professor and you learned it using differential forms, how come your professor never told you about A square? Okay? In your course on electromagnetism. Okay, well, let's write it out. A square is A mu dx mu, A nu dx nu, which is A mu dx mu dx nu. But remember that these are anti-commuting objects. So mu and nu, this is anti-symmetric in mu and nu. If I change the index mu and nu, it changes sign. So therefore, in the same trick that we had before, we can write this as a nu minus a mu dx mu dx nu. Okay? Which is, of course, 1/2 the commutator, as you learned in the course on quantum mechanics that Professor Douglas Smith taught last week. It's the commutator, dx mu dx nu. Now, normally, this is why your professors never told you about a square in your course on electromagnetism, because this would be 0 unless these are matrices. But here, it's not 0 because A is a matrix. The A's are matrices. In electromagnetism, they're just ordinary numbers, so the commutator would be 0. Okay? So are there any questions? Yes?
I'm sure some of the other students have this question we were
Good.
going to ask. So Professor Martin had pointed out that this a squared had some physical consequences which were important in particle physics.
Brilliant question.
Can you mention some?
Yes, brilliant question. Very good. So I'll come to that in a second. Okay, very good question. Are there other questions? So as Professor Johnson kept saying, you should now start to make connections between the phenomenological lectures of Professor Martin and this very mathematical lecture. In fact, if you like, because his lectures are phenomenological, I made these lectures more on the mathematical side. Okay. But also, I made it more mathematical to prepare you for the string theory to come. Okay. Oh, really? You mean little strings moving around? Oh, then I'm even qualified to give a course on string theory. Okay. Okay, but let such sort of joking questions aside, let me ask the students if there are any questions. Okay, so if there are no questions, let me press on. Well, the first thing is that, as I said, this is the only thing that there could be. So this is the answer. But, of course, it would be nice to check this. So this is homework exercise also. But I will do part of it for you here. Okay, I'll do part of it here. Okay, so the first thing is to write the transformation law over there, which is A goes into UA U dagger plus U D U dagger. Okay, so that's this thing here. Okay, this equation written in terms of forms. Okay. And the I disappear because I'm using the nice notation of mathematician, which minimizes the number of I's. Physicists have I's all over the place. Okay? So that is the transformation law. And so this, if I have this transformation law, then I can calculate how dA transforms, because we just apply D to this equation. So there's a U dA U dagger, right, when the D acts on this A, plus the D can act on this U, so du A U dagger, then minus U A when the D acts on this U dagger. And then finally, the D can act on this U, so plus du dagger. And then what about the D acting on this? On this U dagger? Well, that was the exercise you just did. When you have two little d's, you get 0. So d squared is equal to 0, right? So there's nothing there. And then here, you notice I've written a minus sign, and this is crucial. And I'll let you figure out that minus sign. Okay? So the homework problem, your job is to figure out how A squared transform, and then you add these two lines, and you will find that F equal to dA plus A squared transform in a very nice way. It transforms like U, F, U dagger. Okay? So are there any questions? Okay? So now if F transformed in this way, notice that it's different from electromagnetism. At first you should be surprised. In electromagnetism, F just goes into F. It does not change. But here F does change. It changes by multiplying by a matrix on the left and a matrix on the right. But on the other hand, this immediately tells you what the Lagrangian is, because if we take the trace of F mu nu with F mu nu, because F mu nu, if I write this out, right, F mu nu would transform like U F mu nu U dagger. So this would transform as minus 1/4 trace U F mu nu U dagger U F mu nu U, and this is 1, and then you use the cyclic property. This U dagger comes around and meet this U, and you get minus 1/4 trace F mu nu F mu nu. Okay. Now what about this nice result? So that's our Lagrangian. What does F actually look like if we were to write it out? Okay, well, we can write it out. It's dA, so it's d mu A nu, d mu A nu, plus A mu A nu, dx mu dx nu. And by the trick that I told you before, since dx mu dx nu is anti-symmetric, this is 1/2 d mu A nu minus d nu A mu plus commutator A mu A nu. So from here, since this is supposed to be equal to 1/2 F mu nu dx mu dx nu, this means that F mu nu is equal to d mu A nu minus d nu A mu plus A mu A nu. Now, if I plug into the Lagrangian that I have written over there, this is very interesting because this extra term, so you see that there's an extra term here, and this, I guess I really should use colored chalk. This is the first time. So this is the new feature from the new feature, not in electromagnetism. We have an extra A mu A nu term. So now if you plug into the Lagrangian is basically the square of F squared. Okay, so I'm being very sloppy here. The trace and the F and so on. The Lorentz indices I'm neglecting. F squared, it's something like dA minus dA plus commutator of AA quantity square. So therefore, we have three kinds of terms. We have dA minus dA squared, schematically. And then we have another type of term, which is dA minus dA times AA. And of course, there's a trace over everything here, plus AA squared. Okay, so because this new feature that is not in electromagnetism, this leads us to new interactions. New interactions. So this is a remarkable feature of the non-abelian gauge field, that this gives a, so this is what you learned in school, right? This is just the already in Maxwell theory, you have this term. So as in my second lecture of my course, this was the gives the propagator of the photon, right? This was the quadratic kinetic energy term. But this is now a cubic interaction term, a cubic and a quartic. So remember the derivation of the Feynman rule. When you have a cubic term like this, if I represent this field by a wiggly line, this gives a cubic interaction like this. So if we go back to the analogy of the mattress, the excitations on the mattress two of them can interact and form a third one. And then this quartic term would give something like this. Okay? So it's at this point that you can start making connections with the phenomenological course of Professor Martin. Okay. Now, this is quite remarkable because it says that the photon, we know, does not interact with itself. But the non-abelian gauge field it does interact with itself. So it's known as, it's a nonlinear, the field, this is called nonlinear in the jargon. Okay? Now, as I said, there's deep connection with gravity as well. So it turns out the graviton, the gravitational field, it also interacts with itself. Now, why does the graviton interact with itself? Because as you remember, the graviton is something that couples to energy momentum. So anything with energy momentum couples to graviton. Okay? So the graviton, therefore, couples to itself. Similarly here, the physics is because the photon carries no charge. The photon couples to anything with electric charge, right? But the photon itself carries no electric charge. But the non-abelian gauge field is different. That is to say, because the non-abelian gauge field itself knows about carries the non-abelian charge. The more sophisticated side remark for the more sophisticated students is that unlike F mu nu, which does not transform in the electromagnetic interaction, in the non-abelian case, F mu nu transforms. So therefore, F mu nu couples to itself, and as expressed by these two Feynman diagrams.
Of charge.
Oh, okay, good question. You remember that, oops, I guess I don't have it here. We have to go back to the discussion of electromagnetism earlier. The concept of charge is that any field that is charged transforms under the gauge transformation corresponding to electromagnetism. So it changes by a phase. So the generalization of the concept of charge, right? When you have charge, it means a field that changes, that transforms. So the generalization of that is that here, a field that transforms under this symmetry transformation by some U that has a non-trivial transformation carries charge. So here, this is an abstract mathematical definition of charge. Anything that transforms under the group carries charge. Okay. Other questions? Yes?
You might see the charge if you expand out the covariant derivative and look at its coupling with scalar.
Right. Exactly. Let me see. Right. Okay. So what Professor Gates is asking is that here I have the fields interacting with itself. Okay? But the field, the non-abelian gauge field, also interacts with the scalar field. Okay. Now, in this course, I've been actually avoiding some of these issues, but here we see how this transforms, because if we remember how the interaction goes, because we remember what covariant derivative is from the blackboard over there, that this is equal to d mu phi minus I a mu phi. Right? So therefore, this, for example, this would contain a term like d mu phi. It contains d mu phi dagger plus stuff. And so therefore, in the Lagrangian, for example, this d mu phi dagger term and this a mu phi term could come together. So in the Lagrangian, it would contain stuff plus a d mu phi dagger and a mu phi. Okay, and we're not going to worry about factors of 2's and i's here. So again, in quantum field theory, when you have a field phi, a phi dagger, and a mu here, this corresponds to, if I make a mu represented by a wavy line, then a mu is, here's a phi field, and here's a phi dagger field. So as we go back to the second lecture of my course, this phi field can annihilate, can be a source for a phi particle, and this could emit the phi particle. So this gives an interaction, a non-abelian gauge field with the phi field. Okay. Now I think I recall sealing. Professor Martin showed me some of his transparencies, and he had pictures like that. So you should remember and make the connection. Now I'm almost running out of time, so I would make a further somewhat mathematical remark, but which I think is also important, is that a remark that was made by 't Hooft, which I think I was going to talk about this in detail, but unfortunately there's no time. So a remark by 't Hooft, which is that this is bad notation. This wiggly line that I've drawn here to represent a non-abelian gauge field, that was the notation that was used by for the photon, and so people naturally use this notation. And 't Hooft says that this obscures the matrix character of A mu. Because we actually know that A mu is a Hermitian matrix, as I mentioned over here. Okay, A mu is actually an n by n matrix. So A mu, if I write the index out explicitly, there's a matrix index A and a matrix index B. Let's call it A and B. So A and B are things that takes on n values if we're talking about SUN. Okay. Okay, any questions? So A mu is actually a matrix. And if you write a single line like this, so 't Hooft said that obscures the matrix character. So what you should do is you should remember that A mu actually carries two indices. So 't Hooft introduced what is called the double line formalism. So instead of writing a single wiggly line, he writes a double line. Okay? So one of these lines carries the index A, and the other carries the index B. So if we were to do that, that cubic interaction then becomes this picture. Okay? And the quartic interaction then becomes this. Okay? So, which is mathematically a much nicer representation of these interaction vertices. So the gauge field is really like carrying a double line coming in. And so I unfortunately ran out of time, but I was hoping to also talk about the large N expansion, but obviously there's no time. So this is a very interesting subject and also has deep connections to string theory. Professor Marov, in his first lecture, mentioned something about ADS, CFT, and all these things, and so on and so forth. So in the development of recent developments of string theory, Lagrangian also plays a very important role. So you may ask, what is the Lagrangian expansion? Well, it turns out that remarkably, you see that there's another, if you like, expansion parameter in the theory, which is n, the size of the group. And what 't Hooft pointed out was that as n goes to infinity, the theory simplifies. So there is some hope, and that why theories like this, by the way, these non-abelian gauge theories, they're called they, for example, known as quantum chromodynamics, as I think mentioned in some of the lectures, the theory of quarks and gluons. Even if we forget about quarks and just have gluons, they're described by these Yang-Mills theory. And turns out that in nature, there's 3 colors, so it's SU3, and that theory, very little is known about that theory. But 't Hooft pointed out that instead of SU3, we could go to SUN. And there's some hope that as n goes to infinity, the theory may become solvable. So this was a very nice idea that 't Hooft introduced, a so-called Lagrangian expansion. And in my book, again, if you have, once this book arrives, gets out of custom, you see that I have a chapter. Chapter 7.4 is devoted to Lagrangian expansion. The Lagrangian expansion is very important. 't Hooft showed that out of the Feynman diagrams, many of them can be thrown away. They scale, they vanish as n goes to infinity. And so the theory simplifies, and there's some hope that the Lagrangian Yang-Mills theory may be solvable. So as I said in the beginning of this lecture, there's really a lot of frustration amongst the lecturers because there's just really so much to cover. And as I said in the beginning of my lecture last week, in my first lecture, I think all of the students here understand that quantum field theory is a very rich and big subject, and there's no way it can be explained in 4 lectures. And I fulfilled my own prophecy. There is no way of explaining quantum field theory in 4 lectures, so I turned out to be a rather good prophet. So hopefully some of you would go on and read a textbook and learn quantum field theory, that this gives you enough of an introduction. Thank you.
Thank you for a really excellent series of lectures.
Oh, thank you. Thank you. What's the physical interpretation? Well, I don't know how to answer that question because it depends on the definition of the phrase physical interpretation. I don't know what that means. So a rather flip answer would be that, well, actually, I can't give you a serious answer. Okay, so first let me give you a serious answer. The serious answer, semi-serious answer, of course. Well, let me first give you the flip answer. The flip... Well, the flip answer is I go back to what I said in my popular lecture, is Einstein's to know the mind of the creator. So the creator likes gauge symmetry and local symmetry. Okay. So a more serious answer is something like this, which I think here I have to consult Professor Ellis. I don't know if it goes back to people like Einstein and Mach and Yang and so on. In Yang's papers, for example, he always emphasized that global symmetry really bothered him. So global symmetry, remember, is the symmetry in which you transform, the transformation does not depend on space and time. This means you have to make the same transformation. If you imagine making the same transformation here on Earth, you have to make it on the other side of the moon and in the Andromeda galaxy and everywhere in the universe and for all time. So the notion of local gauge symmetry is just more appealing to a lot of people. A lot of people think that physics should be invariant under transformation here and transformation there and so on. And Today I make a transformation, tomorrow I can make a different transformation, and so on. And the gauge fields are then the things that propagate that information from one point in space-time to another point in space-time. So this gets into more of a philosophical thing. So it depends on what you mean. So some people are so insistent on this point, some theoretical physicists, is that they say there should be no global symmetry in nature. So some people even use this criterion to throw out papers in, that. First of all, by the way, as students, you notice, I tell you a couple of theorems, which I already alluded to in private conversation with some of the students, is that to first approximations, there's almost an infinite number of physicists. And each physicist writes an almost infinite number of papers because people write really junky papers. So as students, you'll be amazed at how many papers are being written every day. I mean, there's a tidal wave. So as a student, you have to have some selection criterion. With age, you develop this thing called quote-unquote taste, which in first approximation means you only read your friends' papers. And so, but more seriously, taste to students means that you have to develop some of these prejudices. These are definitely prejudice, but a young theoretical physicist should have a lot of prejudice, okay? Okay, in human lives, it's bad to have prejudice, but in theoretical physics, it's often good to have prejudice, okay? So some people have very strong prejudices. So they are just prejudiced against global symmetry. And they say, if I pick up a paper and it has global symmetry in it, I don't read it. I just throw it into the trash can. So some people just insist that there's no global symmetry in nature, that everything is gauged. Now, I don't want to debate this philosophy and whether or not I personally subscribe to it. It's my own private business, right? So.
Okay, so perhaps I'll normalize my expectations.
Right.
Perhaps we would have 5 questions, but
okay.
We should have one more.
Looking at a single line, you could show the difference between the photon and the particles below. The last diagram below.
Here?
Yes. You have shown a difference between the photon and then the particles that are being propagated.
Yeah. So
how do we do that in the double line?
Oh, okay.
Show the difference?
Yeah. So that's a very good question. So it's really a very beautiful subject, this 't Hooft's double line thing. It just shows if you are young, how many things you can think of. So this
because you don't have any prejudice.
When 't Hooft, yeah. No, he actually has strong prejudices that his professor didn't know anything. That was his guiding principle, which turns out to be very true. In the double line formalism, this would be drawn like this. Okay. Now you see in 't Hooft's formalism, this is very, very a very, very natural thing, because if this particle carries some index A, this index A would just propagate through, and if this carries an index B, it would just go through, and this would go back to B. Now I should mention that, as you probably heard in some of the other lectures, the modern theory of quarks and gluons are based on color. The index is called color. And so this index, for example, could be red. So this would be a red quark going into this line. And this could be color green. So this is, in fact, quarks, as you remember, have different colors. So this is actually a process in which a red quark is transformed into a green quark. Yes? Oh, okay, that's a very good question. That's actually related to the question you asked earlier, which is the difference between the SUN groups and the SON groups. So you seem to be quite mathematical, so perhaps you can see it immediately. But for the other students, I leave this as a homework exercise. It's actually very instructive. That in SUN, the two indices are different, actually. One is, as you know, covariant, and the other is contravariant. But in the SO groups, the two indices, the way I think about it, because I can never remember such big words like contravariant or something. So the way to remember it is that in the SUN groups, one index lives upstairs, the other lives downstairs. but in the SON groups, they both live on the same floor. Okay? That's, when you're a student, if the professors use very big words, you should invent your own ways of understanding it, right? That's what Feynman always says. These people with these big words, I don't understand what they're talking about. So just imagine the tensor has two little floors. Okay?
Okay, we should probably stop there, but this doesn't mean you stop asking questions. We all get tea and coffee, and we gather around and we talk to each other.
Yeah.
And we also talk to Professor Z. I'm going to come along with my camera, and whichever group of students happens to be around Professor Z gets in the picture with the students.
I was actually hoping to have a complete set. So I was thinking if I stand, if you stand there, would you be able to take a picture? Or if I stand here, you'll be able to take
you immerse yourself in the middle of the audience, and I'll try and
Or what if I stand? Oh, okay. So sit there in the middle of the audience. Okay. I was hoping to. The reason why I wanted a picture is because 15 years from now, when one of the students wins the Nobel Prize, I can show it to my friends. I said, "Look at this student was in my lecture."
we're wasting time.
Maybe.